Alrighty, so here we are with our Pre-Calc 6.4 lesson on polar coordinates. Alright, so first thing that we're going to talk about here is a Cartesian or rectangular coordinate system, which is what we've been used to up until now. So again, this is just your standard x, y axis. All right. It is, in fact, named after the French mathematician René Descartes, which is Cartesian Descartes. Anyway, and it consists of two perpendicular axes, so that's your x and your y, whose intersection is called the origin. So right here. Alrighty, so again, that's what we've been doing standard. However, now we're going to talk about polar coordinate systems, okay? And it consists of a plane with a point called the pole, and a ray or a bunch of rays, which are your polar axes. The pole is like the origin, so kind of like this, and the polar axes would be the positive x-axis. So there is an attachment to this section, but if you look at this example here, this is kind of what we're talking about here. So again, here is the pole, and then out from that pole are kind of like your x's, okay? And so you go one circle out, that would be the first radius, second radius, third radius, and then from there, other than a radius, which is how you do these coordinates, you're then also told what degree to travel. So then from that point, you would go maybe a certain amount of degrees to actually here. Or maybe you'd rotate a certain amount of degrees to here. So we'll do a few examples in a bit. So polar coordinates, as I just showed, are in the form of r comma theta. This theta was messed up on the sheet. So anyway, r comma theta instead of x, y. R is a directed distance like a vector, okay? And so you're asking how many radii or circles out from the pole. Okay, so if you have an R of 10, that means you're going to go from the pole out 10 circles. Okay, and it's always to the right when it's positive and then to the left. So here we are with a positive R, means travel R units in the direction of that theta. And again, I'm going to mention that that is to the right. And then a negative R means that you're going to travel R units in the opposite direction, but that is to the left. All right, then we have our theta. Okay, so again, it's r comma theta. So theta is the angle in standard position. So standard position starts like the unit circle. So unit circle 0 degrees. And a positive theta is measured counterclockwise. So if you're starting at a 0, you're kind of going to travel around the circle that way. However, negative theta is measured counterclockwise. So if you're starting at 0, you're going to go backwards of the clock. All right, so that is how that works. So trying that out, we are going to rotate around the pole by an angle of theta and count R units towards that theta, or to the right or to the left. So taking a look at this first one here, 2 means that you are going to go right 2 circles. Okay, and then 30 degrees in the counterclockwise direction. So taking a look at where that is going to be, again, from this pole, you're going out 2 radius, which means 2 circles. And then we're going to go counterclockwise 30 degrees, which of course is the regular direction. So we travel 30 degrees and end up right here. So that is A. All right. The next one wants you to go left 2 circles, and then again counterclockwise 30 degrees. So now we're going to go left 2 degrees, but then remember clockwise would go this way. So if we're left 2, then we want to go counterclockwise. And each of these is worth 15. So if I'm going to the left 2 circles and then down 15, but then another 15 because we're at 30, we're going to end up right there. And that's B. So basically the mirror image of that. Then, again, notice that all of these are either positive or negative of the same thing. This one means that we're going to go right 2, okay? And then also clockwise, negative 30. So right 2 circles, super. And then clockwise from there down 30 units, because positive 30 would be this way. So negative 15, negative 30 would be right here. It turns out that all of these have actually 4 different coordinates. And so in the next example, we'll give 4 of the same coordinate for 1 point. So then we have our last one here, which is negative 2. So again, that's going to be left 2 radii. So we're going from the origin or the pole, left 2. And then from that point, we're going to go clockwise. So again, a clock moves this way. We're going to go clockwise 30 degrees. So 15, 30. And so that's where point D is. All right, so again, very similar coordinates with a negative and a positive. And notice that we get completely different points. So gotta be careful. All righty, then we are going to talk about coordinate conversions. So we did this when we were talking about things in parametric mode, but now we're doing coordinates in polar mode. So polar coordinates are again r comma theta, and rectangular coordinates or Cartesian coordinates are x comma y. So there is a way to convert between one and the other. X and y is pretty direct. All you need to do is take the r value, which they give you, and times the cosine of theta. If you want the y value, you take r times the sine of theta. You do, when you are doing this one, want to graph the original. So maybe we'll put our little star here. We want to always graph the original coordinate. And note the quadrant. Because you want to repeat that same quadrant when you're actually making it. So for instance, in our last example, if I was going to make this polar coordinate into a Cartesian coordinate, I want to make sure that when I get my result, it's up here in quadrant 2. Quadrant 1. Okay, so if it's not in quadrant 1, then you need to change around your negatives and positives, whatever it is, in order to get it back up into quadrant 1. All right, the rectangular to polar coordinates, again, as I just mentioned, there are 4 ways to write every polar coordinate. And so that is why it's very helpful to graph the original coordinate point in order to figure out what quadrant you're trying to make this polar coordinate into. So again, you either have the option of a positive or a negative of this result, and then a tangent of this, but then you could add or subtract 180. So we'll talk about that one in a second right here. So again, we are given an x and a y, and we are trying to convert it into polar coordinates. So again, we have rectangular, and we're trying to make it into a polar coordinate. So in order to get your r value, you're going to take the plus or minus of the square root of x squared plus y squared. And these equations will be given to you in your equation sheet for chapter 6. So it's all good. So I need to plug in my x of -8 and my y of -6. So r is going to be a plus or minus the square root of -8 for my x and a -6 for my y. But then these two things squared makes 64 and 36. And please don't try to argue with me that your calculator told you that -8 squared is actually -64, okay? Because that just means that you did not, like I have written here, make parentheses. So again, -8 squared without parentheses, and then -8 squared with parentheses is what we're talking about, because it is technically -8 times -8. That was the whole idea, because it used to be x times x. And so now it's just the x value of -8 times -8, versus what the calculator is doing here, which is actually -1 times 8 squared. That's what it reads this as. So we don't want that one because that's -64. No, no, no. All right. So then we take 64 and 36 and add it up, and we realize we have 100. So we're looking for either a positive or negative square root of 100, which is 10. Alrighty. Then I'm writing too big, so now we need to do the theta. So I'll do that on another piece of paper. So here we are with example 2 in the 6-4 notes. Okay, so anyway, we are now trying to do theta, and theta is the tangent inverse of y over x. And so that means that we're going to do the tangent inverse of our y value, which is actually -6, and our x value, which is -8. And when you do the tangent inverse of that, you're going to get a theta of tangent inverse. Don't forget to be in degree mode. You're going to get 36.87. And remember that you could add or subtract 180 to that. So just checking. So when we actually graph the coordinate of -8, -6, -8 goes this way, -6 goes this way. So you're going to be in quadrant 3. So when I'll label this. Okay. So when we graph this next one here on our polar coordinates, we're trying to graph an r of either plus or minus 10 and a theta of 36.87. And so if I want this to be in quadrant 3, let's say that I do a -10, because -10 is going to bring me over to this, okay? So one of my options could be -10. But then in order to get down here into this quadrant, I'm going to have to do a positive 36, because then that will get us in here. Anything below 90 would get us still in this quadrant. So in that case, we're going to do 36.87. So that is one of our options. But now we're going to go through all of them. So another way of getting over here would be to do positive 10. But then this is where the 36 plus or minus 180 comes in. Okay, because if we take positive 10 circles, we're going to be over here somewhere, okay? And then if we rotate 36 degrees, we're only going to be like here. So that's not quadrant 3. So we want to go another 180 degrees in order to get down here. So that means that I want 36 plus 180 instead. And so we're going to be at 216.87. Because again, that was our 36, but plus 180. Okay, then if we want to try negative 10 again. All right, so we're at negative 10 and we want to get here. Instead of doing a positive degree, we could do a negative degree because we could travel all the way over this way to get back into this quadrant at this area. So in order to do that, we're actually going to take 36 and subtract 180, which would get us over here. But then we need to subtract another 180 because we actually want to get into here. So we're going to do 36 minus 360. 36.87. And that means that we are going to travel negative 323.13 degrees. So again, negative 10, but then 313 degrees is going to get us back to where we wanted to go. There we go. Okay. So then the other option is going to be 10. So again, 10, but now instead of going a positive degree, again, we're going to go a negative degree. So negative 36 would be like here, but we actually want to go all the way over here. So we're going to take that 36 and subtract 180. And we'll get negative 143. All right, and so again, 90 would be here, negative 90. Negative 180 would be here, but 143 is going to be in the middle where we want it. So again, this coordinate is in this area. Sorry, this coordinate is in this area, quadrant 3, and we can get there by doing any of these. Clearly, the more easy one is going to be not having to add or subtract 180. So just double checking if you need to have a plus 10 or a minus 10 and then using the degree that you got. But of course, you can get creative here. So those are our options for example 2. We need a little less paper for this next one. All right, and on the next one, we have 345. So if we graph 345, that means positive 3 circles, 1, 2, 3 circles, and then a 45 degree angle from there. So right here, because that's 45. So notice that we are in quadrant 1. Okay, so if we want to stay in quadrant 1 when we're doing these coordinates, we need to make sure that our result is still in quadrant 1. So our x value is going to be r times cosine of theta. And since this is our r and this is our theta, we're going to have 3 times cosine of 45 and 3 times cosine of 45 is 2.12. So that's our x value. The y value comes from r, but times the sine of theta. Hopefully that brings you back to the unit circle. And r is 3, and theta is 45. And that actually gets you, because of sine and cosine at 45 being the same, 2.12 as well. So the rectangular coordinate for this is 2.12, comma 2.12. Okay, so again, a lot easier, but notice that we are also checking that it's in quadrant 1, just like our polar coordinate was. So, and it is, so check for that. All right. So again, converting to polar coordinates is a little bit more difficult. Going to rectangular, nice and simple, but again, always want to check if you're in the right quadrant. Okay, so then we have graph the polar equations. So what we're going to want to do to graph a polar equation is to set our calculator mode to polar. So if you go to your menu key, you're going to get polar. So on my calculator here, I've got my mode, and instead of being in function mode and parametric, which is what we did previously, we're going to be in POL, which is polar. If you press the Y equals, we get these R's now. So isn't that fun? Yay! And then just to double check, make sure that your plots aren't on. So if you see any of them highlighted like that, you want to go up and press enter and get it unhighlighted, because otherwise you'll get a domain error. And then now you'll notice that this key, anytime you type it, it's not going to be an X anymore or a T for parametric mode. It's going to be a theta. So that's new. And then if we press our window, we'll notice that just like in parametric mode, we now have a theta minimum. Okay, so this one just works like the T in the previous. And so if you don't have, for instance, an entire circle in here, you won't get the entire visual of whatever frame you're getting. So you need to know kind of the period of whatever function you're looking at. So that's that. And so we are going to try to graph R equals 3 cosine 4 theta. And again, this is in parentheses here. So in our R equals, we're going to type in 3 cosine 4 theta. So again, your theta is your X key now. And if we go to the window, again, trying to make sure that we have 360 as our degree, the kind of standard window here is -5 to 5 versus 10. But anyway, so if we graph this, we're going to actually see something a little bit more exciting there, a flower. And that's actually what the visual is. You'll notice that yours doesn't necessarily have equal petals like this one does. So notice that each of these kind of have that equal out, versus this one looks really skinny and that one looks fat. That's because your calculator is a rectangle and this is a polar coordinate of a kind of square grid. So if you do want yours to look exactly like this, you can go to zoom and you can go to square, which means that it's going to create a square on your grid. I mean, not visually, but it will create it to be a square. And so in that case, each of the petals is now the same area. So again, that zoom square to get it nice and perfect. So, the next piece here is to name 4 different pairs of polar coordinates. As I just mentioned, that you can name any coordinate in 4 different ways, depending on what's happening. So the first one here is on the degree polar coordinate versus the radian. So notice that we're over here at angle 300 and you're on the second circle out. Okay, so 300 degrees is where the line is, and then it's also 2 circles out from the pole. Okay, so in order to write these down here, the first one is going to be just trying to do positives as much as possible. So 2 circles out for one of the coordinates, and then trying to do a positive degree. So even though you want to do over here, which, okay, let's do, you're going to go negative. Each of these is 15, negative 15, 30, 45, 60. So negative 60 degrees. So over 2 circles, down 60 degrees. But notice that it's also at 300. So we could go over 2 and then 300 degrees. So instead of over 2, we could go to the left 2. Okay, so if we go to the left 2 to get over here, we'd need to go 15, 30, 90 to here, and then another 30. So 110 degrees in the positive clockwise direction. Sorry, positive counterclockwise direction. Counter, yep, okay. Or we could go negative 2, and then instead of going this way, we could go 180 degrees plus another 60. So 240 degrees in the positive direction. In the negative direction. Because again, going clockwise is negative, and going counterclockwise is positive. And the reason this is folded is because I have these answers here. So anyway, same answers below. All right, then the next one, and these ones are a little bit harder just because they're in radians, but either way, it still works. So we're trying to get this dot over here. So that means that in order to get it, maybe keeping positive, we are at 7 pi over 6. But we're also, how many circles out? 1, 2, 3 circles out. So that means if I want to try the positives here of going 3 circles out, I need to rotate all the way to 7 pi over 6. That's not so bad because it's exactly what we were given. Kind of like here, but we didn't go positive first. All right, so then we're going to do 3 again, but now we're going to try to go this way. And so this travel here is the same as if we were to travel to over here, 5 pi over 6. So we're going to say negative 5 pi over 6. I just always have to check in the degrees if I'm going negative or positive. All right, then we're going to do 2 of them that have negative 3. So meaning that we're going to go negative 3 circles from the pole, and then we're going to go down 2 to get here. And so remember that rotating counterclockwise is going to be positive. So if we go down 2, that's technically the same as going to this direction. So pi over 6. And then if we go negative 3, but then rotate all the way over here, that means that we're going to go a distance of 11 pi over 6, and that's in the negative direction. Now, if you don't like radians as much, you can, of course, convert all of these to degrees, and just note that this would have been at 210 degrees versus at 7 pi over 6. So, and again, this was folded in half because all the answers were here as well. All right. So you should be able to work through your assignment. This list is on HeadRush. You can go there. You should try this assignment. Maybe take a look at the answer key. And then if that doesn't help, go through the assignment video solutions where I work out every problem. Woohoo. All right. Good luck.